Okay. All right. So now we're going to talk about probability. This, what I'll do in probability today is actually not in your primer, but it is very important, and I use it as a basis for the statistics. So I thought we have enough time to do that, and we'll do that well, and then we will do the statistics later in another session. But everything we'll do in statistics is covered in your primer. Okay, so both probability and statistics are rigorous ways of thinking about uncertainty. And of course, a lot of the sustainability science or management that you have to deal with involves uncertainty. In fact, almost all of it does. And so probability and statistics provide a useful tool to handle that uncertainty. Okay? And so that's why you need to get used to it. And it should be actually central to the way you think, even though when we teach many things, both in the sustainability science and in management and economics, the uncertainty part comes later. Usually we start off with simple examples that don't have uncertainty, that are deterministic. And then we add the uncertainty. But the real world uncertainty is central. It comes before anything else. Okay, so once you've learned to walk with the uncertainty, you have to get used to incorporating that uncertainty all the time. You know, I've learned with this ankle problem that walking is really just a series of controlled falls, and you don't realize that after you learn to walk, right? You forget that you're just falling all the time. And that's what uncertainty should be like. You should incorporate it, and you should realize in your analysis that you're just making mistakes all the time. Everything you say is really probably wrong. But nevertheless, you have to incorporate that. You have to control your mistakes, just like you control your falls. And that's really what management is about, controlling that uncertainty. Okay, so these are methods of control. We think of a sample space as a list of possible outcomes. So we imagine that uncertainty and we control it, we bound it, we parametrize it. A parameter is something that bounds something, like a perimeter fence. Those two are etymologically linked. The sample space is a parameter which bounds our uncertainty insofar as it lists all possible outcomes that we imagine for the uncertain set of outcomes. An event is a set of possible outcomes. So, for example, if you think of the uncertainty as throwing a dice, throwing a die, a single die, then the list of all possible outcomes would be 1, 2, 3, 4, 5, and 6. An event would be a list of possible outcomes within that list of all possible outcomes. So it might be getting a number less than 3. Okay, so that event would consist of the outcome 1 and the outcome 2. Two outcomes, two possible outcomes, adding up to the event getting an outcome less than 3. Okay. Relative frequency is the relative frequency of an event A is the proportion of times that event occurs in some fixed number of trials. Okay, so if I were to throw the die 100 times, and I were to compute the relative frequency, the proportion of times in those 100 trials I got the event A, that would be the relative frequency. Let's say that I got it 30 times out of 100, then the relative frequency is 30 over 100. The probability of event A occurring is the relative frequency of event A as n goes to infinity. So as I run that trial repeatedly with no change in structure except the new realizations of the uncertainty, the limit of that relative frequency is the probability. Okay. Okay. Now, there's some properties of events that we're going to find useful to talk about. One is mutual exclusivity. Two events, A and B, are mutually exclusive if and only if the probability of A or B, okay, and A or B has a very specific meaning in probability, and that specific meaning is the probability of A or B is the union, is the probability of the union of events A and B. Okay? That means either A occurs or B occurs, or A and B occur. Okay, so the probability associated with those three is the probability A or B, also known as the probability of A union B. Okay, so you've all probably done set theory in high school or early college, right? So this should not be new to you. Okay? Okay. If this rectangle represents the sample space, that's the list of all possible outcomes, and I have outcomes A, this is event A, that's a set of outcomes, and event B, another set of outcomes. These two events are mutually exclusive because there are no outcomes which comprise both event A and event B, right? So in that case, the probability of A or B is the probability of A. You could think of it as the area of this first circle plus the probability of B, the area of the second circle. It wouldn't always be the area. If the probabilities were uniformly distributed over this space, then you could think of it as area. But otherwise, it would be some function of that area. Okay. But, of course, events that are not mutually exclusive might look like this. In that case, the probability of A or B would not simply be the sum of these two circles, because you'd be double counting the intersection, right? So by definition, events A and B are mutually exclusive if and only if the sum of their probabilities gives you the probability of their union. That means the probability of the intersection is null. Okay? Collectively exhaustive are events A or B or C are collectively exhaustive if the union of all those events is the sample space, or the probability of the union of all those events is equal to 1. Okay, so the example here would be suppose this is the set A, this is the set B, and this is the set C. Okay, so A, B, and C would be collectively exhaustive and mutually exclusive. Okay, when a set of events are collectively exhaustive and mutually exclusive, they are also known as a partition of the sample space. Okay, you can see that A, B, and C are a partition of the sample space in casual language. Okay, and yes. Yes, the three-line symbol means by definition. Okay, so that's the probability of A or B or C is by definition probability of A union B union C. Okay, good question. Okay, now a couple of probability axioms I'm sure you've met. That is, if you have a discrete valued variable x, so now I've gone away from this sort of Venn diagram and I'm thinking of my uncertainty in the following structure. It is uncertain in that I have some variable capital X and it can take on a particular value little x and I don't know what value it's going to take on. Okay, so my uncertainty is that it's going to take on a particular value value x and I don't know what that is. And there's some probability associated with that value, that random variable capital X taking on the particular value little x. If we're talking about a discrete valued variable, then it can take on some value 1 and 2 and 3 and 4 and 5 and so on. Then I could simply express the following axiom, that is, the probability that x takes on a particular value has to be less than or equal to 1 and has to be greater than or equal to 0. Okay, it can't be a negative number. The sum of all those probabilities for all possible values of x has to be equal to 1. Is everyone familiar with this notation, sigma, right? Over all possible values of x. Okay? Okay. Here, these are the Venn diagrams which we talked about. Here we were talking about mutually exclusive events. Now we have two events that are not mutually exclusive. This is the union A union B, and this is the intersection. The red area is what's being denoted, hence the red lettering. This is the intersection. Okay, and now we're not talking about events which are mutually exclusive. So the probability of A union B, or A or B, is the probability of A plus the probability of B minus the intersection probability, right? Of course, if A and B are mutually exclusive, then that's 0. Okay. This is something, how many people have had to deal with SQL queries? You have, right? So this is a very useful thing to keep in mind. There is the concept of the exclusive OR. In natural language, the word OR never implies the exclusive OR, but occasionally people confuse it as such, and so this concept is very useful. So this means the exclusive OR means either A or B, but not both. Okay? And so when you do SQL code, often this is a useful query to run. And that is the sign for the exclusive OR. Okay, so a couple of notation things here. This is the sign for the exclusive OR. This is A or B, which would be this whole area, intersected with the complement of A intersection B. So this apostrophe denotes complement. And complement is everything in the sample set that's not in this. Okay, so if I were to take A intersection B, which is this, find the complement of that, that's everything that's not in this. So it's all of that. And I were to take the intersection of that with A union B, then I'd be left with this exclusive OR. Okay. All right. Let's talk about conditional probability. Usually we care about conditional probabilities. We want to know if something has happened, then what is the probability that something else will happen? For example, there is some probability that it will rain on a random day, if tomorrow is a random day. But if I told you that tomorrow is a day in April, chances are the probability that it'll be rain will be different, will probably be higher than if tomorrow was a random day throughout the year. Right? April showers bring May flowers. So there, the condition is that it's April. The conditional probability is that it is, is the probability that it'll rain given that it's April. Okay, obviously that's different. Oh, here I had a more pertinent example, perhaps certainly not more amusing. Okay, so probability of a tanker spill, an oil tanker spill, given that the captain of the tanker is drunk. Okay. Okay, so the conditional probability is given by, is denoted as follows. The probability of B given A, so this line again denotes given, is the intersection probability divided by the probability of the given event. Okay, and you can see that, of course, okay, so probability of A is the horizontally shaded area, and the probability of A intersection B is the cross, what shall I call this? The checkered area, right? So the probability of B given A is this checkered area divided by the horizontally shaded area. Okay, so it's this divided by this whole circle. Right? Knowing that A has happened, knowing that the sailor is drunk, the probability of this tanker spill is this divided by that, not this divided by the whole thing, right? So it's going to be higher. The conditional probability is going to be higher in this case. Okay, suppose a die is rolled. Okay, and event A is the roll takes a value less than 4. And event B is that the roll is an odd number. Okay, what's the probability of the roll being an odd number? That is, what's the probability of event B given that event A has occurred, right? So I'm looking exactly for this quantity, probability of B given A. Well, define the events. Event A is roll takes a value less than 4, so that's 1, 2, or 3. And event B, the roll is an odd number, so that's 1, 3, or 5. Okay, so of the three values that make up event A, 1 and 3, these two values are associated with event B. Okay, so outcome 1 and outcome 3 is in this intersection. Okay, so the probability of event B occurring given event A is these two out of the three possibilities. Okay, this and this out of the possibilities 1, 2, and 3. So you would know that the conditional probability is 2/3. But let's just use the formula. Okay, we want the probability of the intersection. Okay, so that means events A and B occur. That's the 1 or the 3. So you get 1 with probability 1/6. You get 3 with probability 1/6. The two are independent. So the sum of these is going to give you 1/3. So that's 1/3. Probability of an A is 1, 2, or 3. Well, that's just going to be 3 outcomes out of 6. So that's half. So probability of B given A is 1/3 divided by 1/2 using, I must have given you this formula, right? There's the formula. 1/3 divided by 1/2, which is 2/3, right? Yes.